My name is Marco Chaidez, and I will be narrating Chapter 1 and 2. All measured numbers consist of a unit and number. When we are converting quantities, such as miles to feet, we use conversion factors, which are ratios used to express a quantity in different units. We always estimate the rightmost digit when dealing with measurements. Significant figures are the digits we record which are certain and uncertain. The greater number of significant figures in a measurement means the greater certainty. All digits are significant except zeros used only to position a decimal point. And the general rule for rounding is that the least certain measurement set the limit on the certainty of the final answer. The SI system is based on 7 fundamental units or base units. Units are mass in kilograms, length in meters, time in seconds, temperature in Kelvin, electric current in amperes, amount of substance in moles, and luminous intensity in candela. All other units are derived units which are combinations of the base units. One example is speed, which is meters per second, and is the base unit of length divided by the base unit of time. For smaller or larger quantities, we use exponential notation in powers of 10, such as deci, centi, milli, micro, pico, and many more. An ionic compound consists of oppositely charged ions. A binary ionic compound is the simplest form of ionic compound, which is a compound that consists of the oppositely charged ions of 2 elements. A cation is also a positively charged ion, and an anion is a negatively charged ion. A chemical formula is a notation of atomic symbols and numerical subscripts that shows the type and number of each atom in a molecule or formula unit of a substance. 2 general rules are: one is that the name of the compound is the cations first and the anion second. The second rule is that for all binary ionic compounds, the name of the cation is the same as the metal, and the name of the anion has the suffix "ide" added to the root of the name of the nonmetal. In general, if the metal of a binary ionic compound is a main group element, the A groups, it usually forms a single type of ion. If it is a transition element, the B groups, it often forms more than one.
My name is Pamela Benavides, and I will be narrating Chapter 3 and 4. A mole is the amount of substance that contains the same number of entities as Avogadro's number, 6.022 times 10 to the 23rd. It is the SI unit for amount of substance. The mole lets us count substances by weighing them. The mass of a mole of a given substance has the same numerical value as the mass of the substance. For example, 1 mole of carbon equals 12.01 grams. The weight of carbon is also 12.01 grams. We can convert between amount, mass, and number of substance by using the molar mass and Avogadro's number. These are all very important when running reactions and mixing different substances. A chemical equation has reactants on the left and products on the right. When an equation is balanced, both sides have the same number of each type of atom. Balanced equations show relationships between the reactants. When balancing an equation, you place coefficients in front of the formula to multiply each of the atom that follows. Chemical equations can't be changed, and other reactants/products cannot be added. Precipitation reactions occur when 2 soluble ionic compounds react to form an insoluble product, or precipitate. The precipitate forms because the electrostatic attraction between 2 ions outweighs the tendency of the ions to remain solvated and move throughout the solution. When the solutions are mixed, the ions collide and stay together to form the precipitate. The solubility rules can be used to predict whether a precipitate will form. Amounts of reactants and products are given in terms of concentration and volume. Acid-base reactions occur when an acid reacts with a base. An acid is a substance that produces H+ ions when dissolved in water, and a base is a substance that produces OH- ions when dissolved in water. These reactions can also be referred to as neutralization reactions and are double replacement reactions. Aqueous acid-base reactions involve water as a reactant or product. Acid and bases are categorized by strength, which is determined by how much they dissociate into ions in water. Strong acids/bases dissociate completely, while weak acids and bases do not. Acid-base reactions occur through the electrostatic attraction of ions and their removal from the solution as the product. The ionic compound that results from the reaction is a salt. The cation of the salt comes from the base, and the anion comes from the acid.
My name is Marissa Torres, and I will be narrating Chapter 5 and Chapter 6.
Chapter 5 will cover gas pressure. The force of a gas collision within container walls is known as the pressure of gas. The same idea is the reason we can blow up a balloon or pump up a tire. Pressure is defined as the force exerted per unit of surface area. Atmospheric gases exert a force of 14.7 pounds per inch squared uniformly on all surfaces. If the pressure outside of a container was higher, then there are fewer particles on the inside and less collisions occurring within, decreasing the overall inside pressure. If we experimented with a vacuum in a paint can, once the pressure outside exceeded that of the inside, the external pressure of the atmosphere easily crushes the can. Pressure can be measured by using a barometer or a manometer. A barometer is a 1 meter long tube used to measure atmospheric pressure. A manometer is a device used to measure the pressure of gases in an experiment. A real-life example of a manometer is a blood pressure cuff used in a daily medical setting. Thermochemistry, energy flow. Moving on to Chapter 6, we will discuss energy. All energy we see is either potential or kinetic, and both of these forms are interconvertible between one another. An object has potential energy by virtue of its position and kinetic energy by virtue of its motion. Several other forms of kinetic and potential energy consist of solar, electric, nuclear, and chemical energy on the atomic scale. Internal energy is transferred as heat when systems are at different temperatures and transferred as work when a force moves an object. Heat absorbed by a system or work done on a system increases a system's energy. Thus, heat released by a system or work done by a system decreases its overall energy. The change of an internal energy is measured in joules, and as stated by the law of conservation, or the first law of thermodynamics, the total quantity of energy in the universe is constant. Therefore, energy can change from one form of energy to another, but is never created nor destroyed.
Hi, this is Melissa Cadena, and I'll be narrating Chapter 7 and 8. In Chapter 7, I'll be talking about the nature of light and the quantum model. Nature of light. Electromagnetic radiation is the energy dissembled by electric and magnetic fields that increase and decrease in intensity of a wave. Electromagnetic radiation has three variables: frequency, wavelength, and amplitude. Frequency is described as the number of times a complete wave passes in a given time and is measured in hertz. Wavelength is the distance from one point of the wave to another and can be measured in meters and nanometers. Amplitude is the height of the crest and helps determine the intensity of a radiation. We can use a product of wavelength and frequency to calculate speed, which is the distance it moves in a given time and is known as a constant 2.99 times 10 to the power of 8 meters per second. All this is shown in an electromagnetic spectrum that arranges them into increasing wavelengths from 400 nanometers to 700 nanometers, and each is represented by a different color. The quantum model. The quantum model of an atom is described by three quantum numbers: principal, angular, and magnetic. Principal quantum number determines the distance from the nucleus and energy level. It is represented by the letter n and positive integers and increases its energy as the n increases. Angular momentum quantum number is represented by the integer from 0 to n-1 and is represented by the letter L. It also determines the shape of the orbital and is described by letters in the S sublevels. For example, L equals 0 is known as a S sublevel, L equals 1 as a P sublevel, L equals 2 as a D sublevel. Magnetic quantum number is an integer from negative L to positive L. It is represented by letters ML and determines the orientation. The number of ML orbitals is calculated as 2L plus 1 in a sublevel and n squared in a level. In Chapter 8, I will be talking about the atomic trends. Atomic size. It is described as how closely one atom is to each other. As n increases down a group, the atomic size increases because there is a higher chance electrons will spend more time away from the nucleus. As the sieve increases across a period, the atomic size decreases because the outer electrons are pulled closer to each other. Ionization energy. It is the energy required to move one electron from the outer shell. It will decrease down a group and increase across a period. There are two exceptions to ionization energy. The first one is that group 2 has a higher ionization energy than group 3 because it's easier to remove an electron from an unpaired electron in a higher L value than a paired electron in a lower L value. The other exception is group 5a has a higher ionization energy than group 6 because it's easier to remove from paired electrons than in unpaired electrons due to the repulsive force. Electron affinity. It is energy released when an atom accepts an electron. As n increases on a group, the electronic affinity decreases, and it will increase across a period. There are two exceptions to electron affinity. The first one is that group 1 has a higher electron affinity than group 2 because it's harder to add an electron to a 3p than a 3s. The other one is group 4 has a higher electron affinity than group 5 because it's harder to add an electron that already contains one electron in their sublevel. Metallic character. It is usually described metal characters as being shiny, good conductors, and having low ionization energy. The metallic character will increase on a group and decrease across a period.
Ionic bonding occurs between reactive metals with low ionization energy who lose electrons and highly negative ionization energy nonmetals, resulting in a gain of electrons forming an ion. In the case of ionic bonding, the total number of electrons lost by the metals equals the total number of electrons gained by the nonmetals, meaning there is a complete transfer of electrons rather than a sharing of electrons. On the other hand, covalent bonding is the sharing of electrons between two nonmetal atoms, which means that if atoms have similar electronegativities, covalent bonds are most likely to occur because neither tends to donate electrons, so they share in order to follow the octet rule and become more stable. Even though electrons are shared between molecules in covalent bonds, the electrons shared are counted as belonging to itself. Covalent bonds have weak forces between molecules that account for the physical properties. Molecular shape is defined by the relative positions of the nuclei connected by bonding groups. The same electron group arrangements can give rise to different molecular shapes, some with all bonding groups and others with no bonding groups. We know that the bond angle is formed by the nuclei of two surrounding atoms with the central atom's nucleus at the vertex. Molecules can be grouped into different shapes depending on the number of electron groups and how they are set up structure-wise. 5 electron group arrangements are possible depending on the number of bonding and lone pairs. Some molecules have odd electron atoms, meaning a few molecules contain a central atom with an odd number of valence electrons, so that not all electrons are in pairs. A species that contains an unpaired electron is known as a free radical. Knowing the shapes of molecules can allow you to understand physical and chemical behaviors of the substances.
Chapter 11. Narration by Cheyenne Jurek. Today we are talking about valence bond theory and orbital hybridization. Valence bond theory is defined as a covalent bond formed when orbitals of two atoms overlap and a pair of electrons occupy the overlapped region. There are 4 central themes to valence bond theory. The first, opposing spins of the electron pair, is described as the orbital's region formed from overlapping orbitals that can only fit 2 electrons that have opposite spins. Second, maximum overlapping of bonding orbitals. This determines the bond strength. The larger the overlapped region of an orbital, the closer the electrons are to the nucleus, thus creating a stronger bond. Each element has a different orbital shape and direction, and this depends on the placement of the periodic table. This results in various strengths. Third, hybridization of atomic orbitals revolves around orbital mixing. This is possible when the valence electrons from each atom become new orbitals when bonded to form a molecule. These mixed orbitals are known as hybrid orbitals and are formed by hybridization. Finally, the fourth, the feature of the hybrid orbitals, describes rules of the hybrid orbitals. These hybrids allow maximum overlap to create an overall stronger bond. Certain types of hybrids are formed depending on atomic orbitals mixed. There are only 5 types of hybrid orbitals. These depend on which block each atom is a part of. Molecular orbital theory and electron delocalization. Molecular orbital theory is viewed as a breakdown of molecules into nuclei with orbitals that are filled with delocalized electrons that cover the entire molecule. Molecular orbitals are formed by combining atomic wave functions with molecular wave functions of nearby molecules. By adding or subtracting these functions, we can obtain 2 outcomes, the forming of a bonding molecular orbital or an anti-bonding molecular orbital. The bonding molecular orbital is created when these functions are added together, and which in turn creates a high electron density between the 2, reinforcing the bond and constructing interference. The molecular orbitals are lower energy than the atomic orbital, causing smaller nuclear repulsions and high attraction between the nucleus and the electrons, creating a more stable bond. The anti-bonding is created when the subtraction of these 2 functions cancel. This causes a destructive interference and gives a low density between the 2. Therefore, molecular orbitals has a higher energy than atomic orbitals, causing high nuclear repulsions and low attraction between the nucleus and electrons, creating a less stable bond. Molecular orbitals relate to earlier concepts. Each energy level must be filled in order of increasing energy. They can hold a maximum of 2 electrons that have opposite spins, and orbitals that are equal of energy are half filled with spins parallel before filled. You can also create an energy level diagrams for molecular orbitals where it would be showing energy and the number of electrons for both the atomic orbitals and the molecular orbitals. This means we can also create an electron configuration for molecular orbitals. A molecular orbital still has a bond order, and this can be found by finding the difference between the number of electrons bonding the number of anti-bonding electrons, and then multiplying by half. If the result is 0, then the bond will not form, but if it is greater than 1, a bond will form. The higher the number, the higher and more stable a bond will be.